Hello everyone, I'm Akhilesh Kumar Srivastava from ABES Engineering College, Ghaziabad. In today's lecture, we will discuss about the topological sort. Topological sort is a simple concept of the graph, which actually relates to the activity networks. So we will first understand what the activity networks are, then we'll do the topological sort for the given graph, and then finally we will code this using the C++ STLs. So let's say this is the graph given to you. In this graph, you can see that there is no cycle in the graph. Another thing is that this is a directed graph. And if I say that for this graph, 0 and 7 are, or every single vertex in the graph is representing the activity. And each of the activity is dependent on some other activity. For example, if I say that one number is the activity, then one number depends on the activity number 0. Once the activity number 0 completes, then only the 1 can start. Similarly, the 4 number activity is dependent on 1 and 3. So if 1 and 3 completes, then only 4 can start. The activity number 5 is dependent on 7 and 2. So if 7 finishes and 2 finishes, then only the activity number 5 can start. Similarly, 6 number activity is dependent on 5 and 4. So the 6 number activity can start only if 4 and 5 have finished. So in the given graph, the vertices are representing the activities and the edges are representing the completion of those activities. If I arrange these activities in some order such that that order depicts that which of the activity takes early and which of the activity proceeds them, it means that which of the activities starts early and which of the activities starts later, which are the activities dependent on which of the other activities. The sequence of that will be termed as the topological sort. For finding out the topological sort, there are two methods to do so. One is using the DFS and the other one is using the BFS. So we will employ the mechanism of BFS in this lecture. You can study the DFS methodology by yourself. So for finding out the topological sort order, we will have to find out the in degree of each of the vertex. So let's say we will have to find out the in degree. I hope you already have seen my previous lecture when I told you that how to find out the in degree of the vertices in the graph. So for finding out the in degree, we take a direct address table. We initialize all the values of the direct address table as 0. And then we see that what are the connections from the different vertices. From 0, the connection is 1 and 2. So 1 is incremented by 1 and 2 is incremented by 1. From 1, the connection is to 4. It means edge is from 1 to 4. Hence, we increment this value by 1. Similarly, 1 by 1, when you will do so, you will find out all the connections from one another. So let's say that we are going to represent the adjacency list here. And the connection from 0 is to 1 and 2. For 1, the connection is only 4. For 2, the connection is 3 and 5. For 3, the connection is only to 4. From 4, the connection is only to 6. From 5, the connection is only to 6. From 6, there is no connection. From 7, there are 2 connections. That is for 2 and 5. So let's count. The number of the connections should be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 connections are there. So this is representing the adjacency list for our graph. After this, we will have to take a cube. And the cube must be of the same size as that of the number of the vertices. Let's say that we have represented the in degree of each of the vertices here. Let's say the vertices are 0, 1, 2, 3, 4, 5, 6, and 7. The in degree of 0 is 0. In degree of 1 is 1. With the help of the graph also, you can just find out. In degree of 2 is 2. the vertex number 2 is dependent on two activities, 0 and 7. Hence, the in degree of 2 is 2. Then in degree of 3 is 1. In degree of 4 is 2. Then in degree of 5 is also 2. In degree of 6 is also 2. And in degree of 7 is 0. So the in degree of these vertices are actually representing or actually depicting that which of the activity is dependent on which other, or how many activities are actually dependent. Now you can see with the help of the in degree that there are two vertices which has the in degree 0. So those are the activities which can start by themselves automatically. So those are 0 and 7. So we add these two activities in the queue, and then we delete the first value from the queue, and we see the connections from 0. So the connections from 0 are 1 and 2. So we decrement the in degree of vertex number 1 and 2 by 1. So the in degree of 1 is reduced to 0, and in degree of 2 is reduced from 2 to 1. The other activities has the same in degree. Since we already have included the 0 in degree vertices, we do not need to include them again. So in this activity, I found that vertex number 1 is also having in degree 0. So we include that also in the queue. Fine. After this, we delete another value, that is 7. And let's see the connections from 7. The connections from 7 are 2 and 5. So we should decrease the in degree of 2 to 0, from 1 to 0. And for 5 also, we should reduce it by 1. So this becomes 1. So in this process, the activity number 2 has the in degree 0. So that should be included in the queue. From queue, we are now removing this 1. So from 1, the connection is 4. So reduce the in degree of 4 from 2 to 1. So in this process, I did not get any of the edge, any of the vertex which has the in degree 0. So let's delete another value from the queue, that is 2. So the connections from 2 are 3 and 5. So reduce the in degree of 3 from 1 to 0. And for 5, reduce it from just a minute. We will have to draw the line just to ensure that everything is going fine. So for the connections from this 2 is 3 and 5. So for 3, it should be come down to 0. And for 5 also, it should come down to 0. So in this process, the vertex number 3 and 5 have got the in degree 0. So they should be included there in the queue. After this, we are going to remove this 3. So 3 has a connection 4. So let's reduce the in degree of 4 from 1 to 0. Rest of the in degrees will remain same. So in this process, I got the in degree of 4 as 0. So that should be included in the queue. We are removing the 5 now. 5 has a connection 6. And 6 has the in degree 2 as of now. So let's reduce it to 1. So we did not get any of the vertex which has the degrees in degree 0. So let's remove this 4 from the queue now. The 4 has the connection 6. So now the 6 in degree will be reduced from 1 to 0. And since it has got in degree 0, that should be included in the queue. So since we have got the in degree of 6 as 0, and we have included that in the queue, when we remove this 6, there are no connections from 6. You can see that the in degree adjacency list of the 6 is empty. So the queue becomes empty, and here the process stops. The order in which we have included the vertices there in the queue is the topological sort order. So 0, 7, 1, 2, 3, 5, 4, 6 is the order of the topological sort. Now let's try to write the algorithm for the same. Let's say we are writing the algorithm for this topological sort. So topological sort is the name of the algorithm that we're going to write. We already have the adjacency list with us. The adjacency list has a size n. Let's say that we first find out the in degree by the method that we were suggested. Let's say that the in degree is already prepared with us. The in degree vector is n. will employ the mechanism that was used in the last term to find out the n degree of the given vertices. Let's take a queue, and name of the queue is, let's say, queue, and let's initialize this queue so that it contains 0 elements. So to start with, for all the elements, let's say for all or all I that is in the n, if the in degree of the vertex number I is 0, then that vertex should be included in the queue. So we should enqueue that vertex in the queue. So I number vertex should be included in the queue. Now, once we have included all the 0 in degree vertex in the queue initially, then our process will go by the time queue is not empty. So while not is empty queue, my process will go. We should first try to remove the element from the queue. So let's dequeue an element. Let's say that element is X. We'll now look at all the connections which are from X. So for all or for each, let's say J, that is adjacent to vertex number X, you should reduce the in degree of this vertex J by 1. So in degree of J is equals to in degree of J minus 1. If in this process, the in degree of the given vertex J is equal to 0, if this becomes 0, then you should include this vertex in the queue. So you should enqueue this vertex in the queue. Now, immediately after doing the deleting the value from the queue, you can print this, or you can print this after the loop also. So you should write the value of X, which is representing the value deleted from the queue, and the order in which the elements are deleted from the queue will be same as the order in which we have inserted the data value in the queue. And this actually represents the topological sort order. So this is the algorithm for the topological sort. I hope you must have understood this, and we should now do the programming of the same. So this is the program that we did on the last term. We have taken the input from the user for the graph. This is the directed graph. And after this, we have printed this adjacency list. After printing the adjacency list, we have found the out degree and the in degree. Since the out degree of no use for us, so we can just remove this out degree and we will focus on the in degree only. So let us forget about the out degree. That is not for our use. We're not going to print that also. We're not going to print the in degree also. The in degree has been found. We will utilize that for the topological sort. So let's take a queue of the integer data value. Let's say the name of the queue is queue. So for integer I is equals to 0 and I is less than n, means every single element or every single vertex which has the in degree of 0 will be included in the queue. So I will push the data element I in the queue if the vertex number I has the in degree 0. So this is the initial activity that we're doing. After doing so, we'll process the activity by the time there are elements in the queue. So while queue dot size is not equal to 0, we'll keep on doing our activity. Let's take the front value from the queue in some X variable, and let's print this as the topological sort sequence vertex, followed by a space, and then let's dequeue the element. Dequeue is represented by the pop in the C++ STL. Now we'll look at the connections from the vertex number X. So for integer, j is equals to 0 and j is less than adjacency list x dot size and then j plus plus. Let's say the connection is y. It means adj xj is the vertex number y. What we'll do, we will decrease the value of its in degree by 1. So in degree of y will be reduced by 1. So in degree of y is equals to in degree of y minus 1. After this, if the in degree of vertex number y has become 0, so this vertex should be pushed back in the queue. So q dot push vertex number y. So we are just going to check it 1 second if everything is written correctly. Yes, one thing should be written here, that we're going to print the topological sort order. So we are going to print the topological sort order from this. This should start in the new line. So the endl, we have taken a queue. Every element which has a in degree 0 should be included in the queue. After this, by the time queue is not empty, we're going to take the front element in x. We're printing that x. And then every connection from x is explored. That connection is y. We are reducing the in degree of y by 1. And if in this process, the in degree becomes 0, that vertex should be included in the queue. So when this process ends, when the loop finishes, we will have all the vertices printed as per the order of the topological sort. Let's try to run this. So we are taking the graph on the right hand side for testing our program. So this has a total of 8 vertices. The edges are 10 in total. So the first connection from 0 to 1, second is 0 to 2, third is 1 to 4, next is 2 to 3, next is 2 to 5, next is 3 to 4, next is 4 to 6, next is 5 to 6, next is 7 to 2, next is 7 to 5. So you can just check that the order which is giving 0, 7, 1, 2, 3, 5, 4, 6 is same as the order that we have actually found. So I think that we have run this program correctly. So these are the references that I took for designing of this lecture. Thank you so much for watching this video.